The other side of this carbonate silicate biological versus inorganic carbon cycle in regulating climate at geologic time scale is which part of the weathering cycle is more important, and what is the role of biology in determining the relative role of inorganic versus organic carbon, right? So this abstract of this paper states it very well. It is widely accepted that chemical weathering of calcium silicate rocks could potentially control long-term climate change by providing feedback interactions with atmospheric CO2 drawdown by means of precipitation of carbonate, calcium carbonate, and that in contrast, weathering of carbonate rocks has not an equivalent impact because all of the CO2 consumed in weathering process is returned to the atmosphere by comparatively rapid precipitation of carbonates in the ocean. We'll see the reaction in a minute. Here it is shown that the rapid kinetics of carbonate dissolution and importance of small amounts of carbonate minerals in controlling the dissolved inorganic carbon DIC of silicate watersheds, coupled with aquatic photosynthesis uptake of the weathering related DIC and burial of some of the resulting organic carbon, suggests that atmospheric CO2 sink from carbonate weathering may previously have been underestimated by a factor of about 3, amounting to 0.447 petagram carbon per annum. This indicates that the contribution of silicate weathering to the atmospheric CO2 sink may be only 6%, and the other 94% is by carbonate weathering. This is a serious discrepancy in the estimates. Therefore, the atmospheric CO2 sink by carbonate weathering might be significant in controlling both the short-term and long-term climate changes. This questions the traditional point of view that only chemical weathering of calcium silicate rocks potentially controls long-term climate change. So I'm jumping a little bit ahead here, but we will come back to this point later on. This is a nice figure that summarizes the processes. So here is the degassing of CO2. There is the calcite precipitation, calcium carbonate. Seafloor spreading tends to create subduction, metamorphosis, and so on of the silicate weathering that we commonly talk about. Carbonic acid in the rainwater is obviously a critical part of this carbon cycle, and there is island arc CO2 degassing that comes out of the middle of the plates like Galapagos and Hawaii, and this is continental arc CO2 degassing, and this is carbonate metamorphism releasing CO2 slower timescales as silicate weathering. What are the reactions? So if we look at the geologic carbonate silicate cycles, CO2 uptake by rock weathering basically happens through this reaction. Carbonic acid and calcium carbonate is going to produce divalent calcium and bicarbonate, and silicate rock weathering, which is always important because we say it takes up 2 CO2 as opposed to carbonate, which takes up 1 CO2, and that's going to produce also calcium ions, bicarbonate and silica, which are all going to wash into the ocean eventually. So calcium and bicarbonate are transported to the oceans by rivers, and there is the atmospheric CO2 concentration. In the ocean, typically marine organisms build calcium carbonate shells and release the CO2 that's taken up here. This is the typical argument made. So there is carbonate precipitation, where calcium and bicarbonate combine to produce calcium carbonate, and calcium carbonate is deposited on the seafloor and buried, and we looked at the details of how much calcium carbonate makes it to the floor, the rain rate, the lysocline, the place where decreasing temperatures, increasing CO2, dissolution of calcium carbonate, and how much escapes to the bottom are balanced. So rain rate and dissolution rates become equal at the calcium compensation depth. Metamorphism, of course, converts the calcium carbonate with silica back into silicate rocks and releases CO2. So the idea is that 2 CO2 taken up and 1 CO2 released, whereas here 1 CO2 is taken up and that CO2 is released when the carbonate dissolution happens. Okay, so that CO2 is released here as calcium carbonate shells are formed. But the idea of this paper that we are looking at, this is the feedback cycle where we have surface temperature changes can change rainfall and change the weathering rates, and we are also increasing atmospheric CO2 and greenhouse gas effect surface temperatures and driving these kinds of loops. On the longer time scale, Earth's surface weatherability in terrestrial environments, including crustal composition, lithology, tectonics, so uplift rates and topography. For example, Himalayas are still growing, and Himalayan rivers carry some of the highest sediments and weathering rates. Continental configuration, so paleogeography, and hydrology and biological alterations, effects of land plants and soil biomass, together determine Earth's surface weatherability. On the other hand, the weatherability of marine environments depends on the rate of formation of new oceanic crust, its bulk composition, abyssal sedimentation rate, and the saturation state of seawater with respect to silicate phases, all of which have likely evolved over the course of Earth's history. So these are the kind of processes we are talking about, what's happening on land, what's happening on the ocean. And for the longest time it was thought that the most of the silicate weathering is happening on land, but now there is more and more evidence that maybe a lot of silicate weathering happens in the ocean as well. So the weatherability in that sense is important both on land and in the ocean. So first, the origin of carbonates in oceans and lake must be questioned when we think about carbonate weathering contribution to climate regulation on long and short time scales versus silicate weathering role. The occurrence of aquatic photosynthetic organisms is probably playing a role in the origin of carbonates in the oceans and lakes. Is it mainly due to silicate weathering reaction, which went like this? It's a shortened form of what we saw here. Oops. So this is the real reaction, but nonetheless. Or is it mainly due to carbonate weathering reaction, where we look at calcium carbonate, carbonic acid releasing calcium and bicarbonates, but the biological role is played in photosynthesis and producing hydrocarbons and oxygen. Because of the much faster kinetics of carbonate weathering, the carbonates in oceans and lakes may originate mainly from this equation and not from this equation. This is the conclusion of this paper, which argues that overall the weathering of silicate rocks only contributes 6% to the total weathering, and the carbonate weathering contributes 94%. That's a massive change in the attribution of weathering to long-term carbon cycle as well as regulation of climate. I wanted to set this up before we go into the other details. So the weathering happens, alkalinity, it takes out the carbon CO2 into these compartments of bicarbonate and carbonate. We have already looked at the carbon cycle reactions in the ocean. You remember there is hydrated aqueous carbon and dissolved carbon. So CO2 plus H2O in the ocean gives us HCO3 minus plus H plus. HCO3 minus can go into CO3 minus minus plus H plus. With increasing CO2 in the atmosphere, we are increasing the acidification, so we are depleting CO3 minus minus, and that removes calcium and that produces problems for silica forming or shell forming species, because carbonate saturation decreases and so on. But before we go there, in this context, just remember that the weathering of carbonate versus silicate the carbonate silicate weathering regulation has to be considered in this context, that maybe we don't know exactly how much silicate weathering versus carbonate weathering play a role in climate regulation at various timescales. So we will proceed with that in mind to how carbon cycle has evolved and how climate regulation has allowed climate to evolve over time. And then we'll come to the future to see how fossil fuel burning is affecting carbon and what that means for carbon capture, utilization, and sequestration. Okay?